Hello, and welcome to Astronomy 100. In our previous segment, we were talking about the nature of light, how to measure it, how to quantify it. And the three important things that we talked about are the speed of the light in the form of a wave, the wavelength of the light in the form of a wave, and the frequency of the light in the form of the wave. And what we talked about is how to tie all that together. Today what we're going to do, or in this segment, we're going to bring this forward to talk about a little bit of the big picture. And I want to introduce a term to you that is a kind of a big mouthful of a term. It is called electromagnetic spectrum. The term comes from the true name for what we call light. If you remember from a previous segment, we talked about how light is referred to as electromagnetic radiation. And the electromagnetic spectrum, the word spectrum means a range of something, a range or a variety of things. And so the electromagnetic spectrum is a really key concept in all of science, as well, of course, in astronomy. And what it represents is the entire range of possibilities that light can exist as in our universe. Light essentially is all the same thing. It's energy in the form of a wave or as a particle that goes from one place to another. But what we've seen in the previous segment is that light can have a different wavelength, and depending upon that wavelength, it'll have a different frequency. So what I want to show you is the electromagnetic spectrum, and we're going to start on the left side and work our way across to the right side. The numbers are not all that important, but the names and the titles up here are, and we'll get to that as we go. You'll notice as we work from left to right, it says gamma ray, then X-ray, ultraviolet. The one that's sideways here says visible, infrared, microwave, and radio. What you're looking at is the names of the realms that represent different types of light from one wavelength extreme all the way to the other wavelength extreme. So let me give you the idea behind this. Light has a particular wavelength that it can be at, and of course the wavelength can be a variety of different sizes. But in our universe, there's a limit to how small the wavelength can be. Imagine two peaks getting closer and closer together, the wavelength is shrinking and shrinking. A wavelength can never be a number of zero. In other words, wavelength can never have zero size, because in that instance, when you have a wavelength of zero, the wave collapses in on itself. So all waves of light have to have some minuscule size of a wavelength or larger. If we shrink light to the smallest possible wavelength that we can ever have without it being zero, that type of light is called gamma ray light. Now going to the other extreme, radio is sort of the opposite. If we take light and have its have a wavelength that becomes bigger and bigger and bigger, there is obviously a limit to how far apart we can pull the peaks or the valleys. If you pull two peaks to a distance of infinity, in other words, infinitely far apart from each other, then the wave is no longer a wave, it becomes a line. So the limit to how physically far apart a wave peak versus another peak can be, the very, very biggest it could possibly be, is the limit to the biggest wavelength our universe can produce. And that is what we call radio. So gamma ray is the shortest wavelengths that light could ever have, and radio is the longest wavelength that light can ever have. Going back to our picture here, we can obviously have anything in between. So when the wavelength gets bigger and bigger and bigger, what's happening is the light itself takes on different behaviors, and it has different utilities that we use in our scientific world and in our everyday life. So what we do is we give this increasing size of the wavelength, we give it a different name when the light takes on different properties. So gamma ray is very, very short wavelength light. X-ray is a little bit longer, still very short, but a little bit longer than gamma ray. Ultraviolet is longer still. Visible is longer. Infrared longer still. Microwave. And then the longest you could possibly have, of course, is radio. As I said a moment ago, the numbers aren't really that important, but notice the labels here. as we go from left to right, the wavelength is becoming larger. But if you remember from the last segment, wavelength and frequency are inverse to each other, meaning when wavelength gets bigger, frequency has to be getting smaller. And so you'll notice that the arrows are pointing in opposite directions. When we put all this together, and we put these three things together here, what you'll notice is gamma ray light is the shortest possible wavelength. It is the highest possible frequency. Going all the way to radio, radio is the longest possible wavelength that light can have, and it is the lowest possible frequency. So the electromagnetic spectrum excuse me, is a range of all the possible wavelengths that light could have, and of course we name the realms based on the utility of the light itself. You may have heard of radio light. I'm sure you've heard of microwave light, infrared light. Maybe you went to the dentist and had an X-ray. X-ray is light of a very short wavelength. So the electromagnetic spectrum is very important to astronomy because it's all possible forms of light that exist in our universe. What I'm going to do is bring in the idea of visible light. Visible is actually this tiny little realm right in here, and I'm just going to make it larger so you can see it. If we had the ability to see the colors that go with the wavelengths, this is what you would get. Remember, short wavelength to long wavelength all the way to the end. So shortest wavelength light is color that we call violet, and then the longest wavelength light is the color that we call red. So when we go from left to right, we're going from violet all the way through red. So all we're simply doing is changing the wavelength of the light, and of course, as your brain perceives different wavelengths, it shows you different colors. So this is where what we see, this is everything that you will see in the world around you. This is what your brain can perceive. Your brain cannot perceive any wavelength shorter than about 4,000 angstroms, and your brain cannot perceive anything longer than about 7,000 angstroms. But here's what I want you to notice. Notice how what we actually see is just a small part of the light that our universe is capable of producing. There's an enormous amount of light that is just working its way through the universe that we will never perceive. If radio light goes into your eyes, you won't notice it. Your brain doesn't perceive it. If ultraviolet light goes into your eyes, your brain won't perceive it. So what we have slowly discovered over the centuries is that what we see in the universe is actually just a very, very small part of what the light of our universe can possibly be. And what will go with this, of course, as we learn more and more material, is astronomers have learned to take advantage of every one of these realms. We have radio telescopes that are examining the universe in radio light. There are microwave telescopes, infrared telescopes, of course the optical telescopes that we see with our eyes with, and then we have ultraviolet, X-ray, and gamma ray. All of these realms have observatories and telescopes that are dedicated to the ability to see the universe in these wavelengths. Now, to sort of summarize, let me show you what we mean by these things. So here is a bit of a summary to help you remember. Remember that the longer the wavelength is, the lower the frequency. The shorter the wavelength, the higher the frequency. So those two are inverse to each other. The last thing that I want to work our way through when it comes to understanding the nature of light is how are the wavelength, the frequency, and the energy of the light related. So we're going to tie in the concept of energy. To do this, let's bring Albert Einstein into the mix here. Albert Einstein, of course, very famous scientist. He was somebody who lived until 1955, but he became very, very famous in the world and, of course, in the United States in the early part of the 20th century. And most of what Einstein is very famous for today was work that he did in just the first couple of years of the 20th century, 1900 to 1905. And one of the things that he discovered had to do with the nature of light, and this discovery ultimately wins him the Nobel Prize. The discovery that he makes is a way to describe light in a way that becomes very, very useful. Let me show you what I mean by that. Einstein said, let's return to the idea that was proposed by Isaac Newton. If you remember from a previous segment, Isaac Newton said, it is perfectly acceptable to think of light as a packet or behaving as a packet of energy that goes from one place to another. So in this example here, this flashlight being turned on, the light that leaves the flashlight and hits the wall, you can think of it as each of these is a little packet of energy traveling across the room and hitting the wall. Each of these packets of energy travels at the speed of light, and if you remember, we signify the speed of light by the letter c. And Einstein says, let's refer to these as photons. The word photon comes from the word photo, which means light, and so a photon means a little particle of light, is essentially what you would translate that into. Now, Einstein said, if we think of light as particles or behaving as particles that we're going to call photons, he said we can then describe the energy that the photon carries. So each of these photons has an energy that the photon is carrying from one place to another. Photons are energy carriers. The formula that you see down here at the bottom of the screen is showing you how we determine the energy of each of these photons. In this formula, the letter H is a constant. We don't really need to worry about it. It's called Planck's constant, and we can just consider it a constant today. And if you remember from a previous segment, the speed of light is always a constant. So the top of this is just a number that never changes. And you'll notice the bottom is lambda, the symbol for wavelength. So what we have is the energy that the photon carries related to the equivalent wavelength if we describe the light as a wave. Notice how these are inverse. When lambda gets big, E becomes small, and when lambda becomes small, E becomes large. What that translates into is light with a very, very short wavelength is light of photons of very high energy. Small lambda, big E. Light that is a very long wavelength makes E very, very small, which means light that is of a long wavelength are photons of low energy. If we were to translate this to the electromagnetic spectrum, we could see how different types of light could be the equivalent of photons carrying different amounts of energy. Sometimes people have a hard time understanding the idea of a photon being an energy carrier. So what I'm going to do is show you what we mean by this. This is what's called the bucket analogy, In this analogy, think of the bucket as a photon. Obviously, a bucket is something you can carry water with, in this instance if we're carrying water, or carry anything with. So a bucket is a carrier. If we think of the bucket as the carrier of energy, then the bucket is a photon. So this bucket is a photon, this bucket is a photon as well. The energy that the bucket carries is represented by how full the bucket is. So in this case, you'll notice that it's filled all the way to the top, the maximum amount that it can possibly carry, and this would be the equivalent of a gamma ray photon, a photon that carries the maximum amount of energy that a photon can carry. This would be the opposite. This is a photon carrying the least amount of energy that it could possibly carry, just coating the bottom a little bit. And so this would be the equivalent, again, of a radio photon. A radio photon carries the least amount of energy, and a gamma ray photon carries the most. Where people have trouble with this is these buckets carry what's inside of it, but they travel at the same speed. So the energy of the photon is not the speed of the photon. The bucket on the top travels at the same speed that the bucket on the bottom travels. It's just a different amount of energy being carried. So all photons travel at the speed of light at the same speed, but all photons can carry different amounts of energy based on the type of light that it is. What we're going to do is wrap this all together again by showing you the electromagnetic spectrum one more time. And what we're going to do is introduce one final factor across the top here. You notice it says energy, and it has an arrow pointing to the left, high energy on the left, low energy on the right. The idea is, as we go from gamma ray all the way to radio, we are talking about photons of different energy. Gamma ray photons carry the highest amount of energy. X-ray photons carry a little bit less energy, ultraviolet photons less still, all the way through radio. Radio photons carry the least amount of energy that is possible. So the electromagnetic spectrum is also a range of photons with different energies. If I bring up the visible part of the spectrum again, this might help you a little bit because now the idea is still the same. Violet photons are shorter in wavelength than red photons, and so a violet photon carries the most energy for a visible light photon, and a red photon carries the least amount of energy for a visible light photon. And so violet photons carry a lot of energy, red photons carry less. How much more or less? Well, a violet photon is about half the wavelength of a red photon, 7,000 versus about 4,000, close to half. So therefore, a violet photon carries twice as much energy as a red photon does. So when we observe light in the universe, essentially if we think of light in the form of a wave, we can think about all of its properties of a wave. If we think of light as behaving like a particle, a carrier of energy as a photon, we can then now use that property to describe things about life, about the light itself. So what we're going to do is tie all this together and help us understand how to learn about objects at great distances, to remote measure things to figure out what stars are doing and how that light is getting to us. I hope you'll join me.